Testing, can you hear me? Okay, so I'm going to be studying discrete math again. I'm just going to be studying the last two topics. Well, there's a last topic and then there's an additional topic. Study the additional one in the later stream as well. So I finished all of this and I'm going to study chapter 5. And I think chapter 5 and chapter 6 are the only ones remaining. I'll study chapter 6 is generating functions and number theory. I'll study both of them. And that this section contains a lot of detail on what we can say about sets. If you have never seen anything about union or Venn diagrams, it is worth reading this carefully. For us, a set will simply be an unordered collection of objects. So notation, I think this I will rush through. So consider A has 1, 2, and 3. This is read as A is a set containing the elements 1, 2, and 3. Use curly brackets to enclose elements of a set. Some more notation: A is an element of the set A, B, C, and D is not an element. We write X is an element of A when we wish to express that one of the elements of the set is X. For example, consider the set A, which has 1, B, a set containing XYZ, and an empty set. This is a strange set to be sure. It contains 4 elements: the number 1, the letter B, the set XYZ, and the empty set null. How do you pronounce this null? Or do you just say empty set? The set containing no elements. Is X in A? The answer is no. None of the 4 elements in A are the letter X. We must conclude that X is not an element in A. Similarly, consider the set B, which contains 1 or B, even though the elements of B are elements of A. We cannot say that the set B is one of the elements of A. Therefore, B is not an element of A. We have described the set above by listing their elements. Sometimes this is hard to do, especially when there are a lot of elements in the set. For example, if we want A to be the set of all even natural numbers, we could write A is 0, 2, 4, 6, all the way till infinity. But this is a little imprecise. A better way would be X is an element of N. There exists N, which is a set of natural numbers such that X is equal to 2N. Let's look at this carefully. First, there are some new symbols to digest. N is the symbol usually used to denote the natural numbers, which we will take to be the set 0, 1, 2, 3 all the way till infinity. Next, the colon is read such that it separates the elements that are in the set from the condition that the elements in the set must satisfy. So putting this together, we would read this as the set of all x in the natural numbers such that there exists some n in the natural numbers for which x is twice n. In other words, the set of all natural numbers that are even. Here is another way to write the same set. X is an element of n and x is even. Sometimes mathematicians use this or this for such that symbol instead of the colon. Also, there is fairly even split between mathematicians about whether 0 is an element of natural numbers, so be careful there. This notation is usually called set builder notation. Tells us how to build a set by telling us precisely the condition elements must meet to give access. So these are some special sets. You have the empty set and the set of natural numbers and the set of integers, which is z. That includes negative, 0, and positive. Q is the set of rational numbers. R is the set of real numbers. PA is the power set of any set. A is the set of all subsets of A. And then we have, okay, we have this. A is a subset of B asserts that A is a subset of B. Every element of A is also an element of B. A is a proper subset of B asserts that A is a proper subset of B. Every element of A is also an element of B, but A is not equal to B. A intersection B, the set containing all elements that are elements of both A and B, and we have the union, set containing all elements that are elements of A or B or both. And this can be better explained over here. So we have, let's say the set, I will represent set S in this box. So S is 1, 2, 4, minus 5, 6, 10, 15, and 2, 4, minus 5. That's an ugly 4. 10, 15, and 6. Let's do 3 as well, and 0. And then we have set A, which is a subset of S, and A contains 0, 6, minus 5, 15. 0, 6, minus 5, 15. Let's do blue. Now let's do green. 0, 15, 3, 10. Okay. Let's do this. This is B. Set S contains A and B. So we have, yeah, I should write that back. A is this and B is this. B is a subset of S. Now we have A A union B, which is 0, 15, 3, 10, minus 5, 6. And then we have A intersection, which is like union but flipped upside down. 0 and 15. If X A Cartesian product A X B, Is the Cartesian product of A and B the set of all ordered pairs A, B with A and B and B? Okay, okay. A divided by B is the set difference of A and B. It's a set containing all elements that are not elements of B. But I think A minus B is a valid notation, right? It's A minus B. But they're using the slash, which is sets of A that are not in B, so minus 5 and 6. The thing is, they're using slash though. Uh, I've never seen this forward slash. Complement of A is a set of everything that is not an element of A, I think. A union B, complement, everything outside of A union B, 1, 2, 4. And then the cardinality of A is the number of elements. Okay. Cardinality of A is 4. Cardinality of B is 4. Cardinality of S, 4 plus 3 is 7, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. Cardinality of the intersection. We have already said what it means for two sets to be equal. They have exactly the same elements. So 1, 2, 3 is 2, 3, 1. The order doesn't matter. Also 1, 2, 3, 1, 1 plus 1. Okay. 1, 2, 3. 3 is repeated twice. What about sets 1, 2, 3 and 1, 2, 3, 4? Clearly A does not equal B. But notice that every element of A is also an element of B. Because of this, we say that A is a subset of B. So this or this, both symbols are red, is a subset of. The difference is sometimes we want to say that A is either equal to or is a subset, in which case we use subset or equal. This is analogous to the difference between less than or equal to less than. So 1, 2, 3, 4, 5, 6, 2, 4, 6. This is false. This is true. B is an element of C. This is false. This is true. This is true. A is less than D. This is what does this even mean? 3 is an element. The true, false, true, false, true, false, false. A has exactly 6 elements and none of them are empty sets. Oh, this is false. But this is true, right? In the example above, B is a subset of A. You might wonder what other sets are subsets of A. If we collect all these subsets of A into a new set, we get a set of sets which we call the set of odd subsets of A, the power set of A. We write it PA. So let A equals 1, 2, 3, find PA. So PA is the empty set. We have 1, 2, 3, we have 1, 2, 1, 3, 2, 3, and we have 1, 2, 3. Hold on. Think I have a video on this. The cardinality of the power set. So if A has A2, A3, A4. So an empty set would be, the number of empty sets would be 0, choose 0. The number of two elements, so A1, A1, A2, A1, A3. Keep doing two pairs, right? A1, A4. This is uh, cardinality of A. Choose one. No, wait. Yeah, I think that's true. Cardinality of A, the number of elements in A. Choose 0. There's only one way of doing this. Cardinality of A. Choose 2. These many ways of choosing 2. And then we have choose 3. Is power set a set in itself? Yeah, it is. So this thing is entirely a set itself. A choose 3. And then so on. Then we have if we do this, two to the power of this. So 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 we have this, right? Another way to compare sets is by their size. Notice that in the example above, A has 6 elements and B, C, D all have 3 elements. The size of a set is called the set's cardinality. You could write the cardinality of A is 6, the cardinality of B is 3. Wait. Power set. Power set is this set over here. The cardinality of the power set of A is 2 to the power of cardinality of A. Is it possible to add two sets? Not really. However, there is something similar. We want to combine two sets to get a collection of objects that are in either set. Then we can take the union of two sets. Symbolically, it's C A union B. Then we have the complement, the intersection. In another way, okay. Set difference is A intersection not B, and that's this. Having notation like this is useful. We will often want to add or remove elements from sets, and our notation allows us to do so precisely. There is one more way to combine sets that will be useful for us, the Cartesian product. A product B. This sounds fancy, but is nothing you haven't seen before. When you graph a function in calculus, you graph it in either the Cartesian plane. This is the set of all ordered pairs of real numbers. We can do this for any pair of sets, not just real numbers with themselves. So A Cartesian product B, we have the set of all ordered pairs AB. I see. So in this example above, A Cartesian B would be the set 0, 0, 0, 15, 0, 3, 0, 10. 0, 0, 0, 15, 0, 3, 0, 10. I got this right. And then same thing with 6. Voila. 6, minus 5 and 15. Minus 5, minus 5, minus 5, minus 5, 15, 15, 15, 15. So this is the A Cartesian product B. Wait, this is, I think it's called a tuple. I know it's called a tuple in Python, but I don't know whether they call it tuple in math as well. So A Cartesian product B, AXB, AXA, and BXB. So 1, 3, 1, 4, 1, 5. 1 with all of these, 2 with all of these. 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5. This Venn diagrams, this is a very nice visual tool we can use to represent operations on set. A Venn diagram displays sets as intersecting circles. So B, C, and then we have the intersection, the A intersection not B, or equivalently A set difference B. How do you pronounce this? A minus B. We have A set difference B. We have B union C, B union C, and then C, sorry, A, B intersecting with C. So we have all this. Union with C intersecting not A. So C intersecting not A is this. So all of this entire thing. Okay, next. This section contains many details about functions, much of which should be familiar from non-discrete contexts. As you read, consider how the way we talk about functions here might be different from what you know from other areas of mathematics. Function is a rule that assigns each input to exactly one output. We call the output the image of the input. The set of all inputs for a function is called the domain. Set of all allowable outputs is called the codomain. You want to write f is x output y to describe function with name f, the domain y, in the codomain, the domain x, and the codomain y. This does not tell us which function f is though. To define the function, we must describe the rule. It's often done by giving the formula to compute the output for any input. For example, consider the function f n to n. Define f of x squared plus 3. Yet the domain and codomain are the same set. The rule: take your input, multiply it by self, and add 3. This works because we can apply this rule to every natural number and the result is always a natural number. Notice though that not every natural number is actually an output. There is no way that 0, 1, 2, 5, etc. There's no way to get 0, 1, 2, 5, etc. The set of natural numbers that are outputs is called the range of the function. In this case, the range is 3, 4, 7, 12, 19, 28. All the natural numbers that are 3 more than a perfect square. Is it fair to say that a codomain is any superset of the range? The key thing that makes a rule a function is that there is only exactly one output for each input. That is, it is important that the rule be a good one. What output to be assigned to the input 7? Just because you can describe a rule in the same way you would write a function does not mean that the rule is a function. The following are not functions. If n defined by n over 2, the reason that this is not a function is because not every input has an output. What does f send 3? The rule says that f 3 is 3 divided by 2, but 3 divided by 2 is not the element of, of the codomain. Hmm. Consider the rule that matches each person to their phone number. If you think of the set of people as the domain and the set of phone numbers as the domain, this is not a function, since some people have two phone numbers. Switching the domain and codomain sets doesn't help either, since some phone numbers belong to multiple people. Really? How? One phone number for two people? It is worth it is worth making a distinction between a function and its description. Function is an abstract mathematical concept that in some way exists whether or not anyone ever talks about it. But when we do want to talk about the function, we need to describe it. A particular function can be described in multiple ways. Some calculus textbooks talk about the rule of 4, that every function can be described in 4 ways: algebraically, a formula; numerically, a table; graphically, or in words. In discrete math, we can still use any of these to describe functions, but we can also be more specific since we are primarily concerned with functions that have n or finite subset of n as their domain. Describing a function graphically usually means drawing the graph of the function. Plotting the points on the plane, we can do this and might get a graph like the function for the following 1, 2, 3, 1, 2, 3. Wait, what? Okay. The input is in the set 1, 2, 3 and the output is in the set 1, 2, 3. It would be absolutely wrong to connect the dots or try to fit them into some curve. There are only 3 elements in the domain. Curve would mean that the domain contains an entire interval of real numbers. Here is another way to represent that same function. So 1 goes to 2, 2 goes to 1, and 3 goes to 3. So 1 goes to 2, 2 goes to 1, and 3 goes to 3. This shows that function f sends 1 to 2, 2 to 1, and 3 to 3. The arrow diagram used to define the function can be very helpful in visualizing functions. Okay. Note that for finite domains, finding an algebraic formula that gives the output for any input is often impossible. Of course, we could use a piecewise defined function like this: x plus 1, x minus 1, and 3. This describes exactly the same function as above, but we can all agree is a ridiculous way of doing so. Since we will often use functions with a small domain and codomain, let's adopt some notation to describe them. All we need is some clear way of denoting the image of each element in the domain. In fact, writing a table of values would work perfectly. 0, 1, 2, 3, 4, and then 3, 3, 2, 4, 1. We simplify this further by writing this as a matrix. Write each input directly over its input. 0, 1, 2, 3, 4, 3, 3, 2, 4, 1. Now that this is just notation and not the same sort of matrix you would find in in a linear algebra class. One advantage of two-line notation over the arrow diagram is that it is harder to accidentally define a rule that is not a function using two-line notation. So x goes to y, 1 to d, 2 to a, 3 to c, and 4 to b. Each of the following diagrams represent a function. So you cannot have an input giving two outputs. That is wrong. This is fine and this is fine. F is a function, so is g, but not h. Giving an explicit formula that calculates the image of any element in the domain is a great way to describe a function. We will say that these explicit rules are closed formulas for the function. There's another very useful way to describe functions whose domain is n that relies specifically on the structure of natural numbers. We can define a function recursively. Consider the function fn to n given by f0 is equal to 0 and fn plus 1 is equal to fn plus 2n plus 1. Find f of 6. So this is a recursive definition, right? You have 0 over here. When n is equal to 1, when n is equal to 0, we have f of 1. And then we get 1 as the output. F is equal, when n is, okay. Let me just do it in Desmos. F n plus 1 plus 2 n plus 1. F of 0 is 0. Wait. I remember doing recursive function. How did I do that earlier? How did I do that earlier? Where I define recursive functions. Oh, now I remember. I described it recursively in the definition. Wait, hold on. F of x plus 1 is equal to f of x minus 1. The base case is 0, 0. You have 1. It should be minus 1. 1, 2, 6 is 36. Surjections, injections, and bijections. So now turn to investigating special properties functions might or might not possess. The function, okay. In examples above, you may have noticed that sometimes there are elements of the codomain that are not in the range. And this sort of things does not happen. We say that the function is onto or that the function maps the domain onto the codomain. This terminology should make sense. The function puts the domain entirely on top of the codomain. Fancy term for an onto function is a surjective. And we say that an onto function is a surjective function. So every input gets mapped to every element in the output. And this is not surjective. Which function are surjective? F of c equals to c divided by integer to integer. This is not surjective because you cannot get 1 this to this. This is not surjective because you can't get b as the output. This is surjective. Number 3 is surjective. To be a function, a rule cannot assign a single element of the domain to two or more different elements of the codomain. However, we have seen that reverse is permissible. A function might assign the same element of the codomain to two or more different elements of the domain. When this does not occur, then we say a function is one-to-one. Again, this terminology makes sense. We are sending at most one element from the domain to one element from the codomain. Okay. We are sending at most one element from the domain to one element from the codomain. One input to one output. The fancy math term for a one-to-one function is an injective. We call one-to-one functions injective functions. So this is injective, not injective, injective. This is not injective. This is injective because there's an output from two different inputs, but that's not true here or here. Surjective and injective are not opposites. You can see in the two examples above, there are functions that are surjective but not injective, injective but not surjective, both or neither. In the case when a function is both one-to-one and onto, you say that a function is a bijection, but that a function is a bijective function. When discussing functions, we have notations for talking about an element of the domain, say x, and its corresponding element in the domain. We write f of x, which is the image of x. Sometimes we want to talk about all elements that are images of some subset of the domain. We would also be nice to start with some elements that are of the codomain and talk about which element or elements from the domain is the image of. We could write those x in the domain such that f of x is equal to y. But there's a lot of writing. Here is some notation to make our lives easier. To address the first situation, what we are after is a way to describe the set of images of elements in some subset of the domain. Suppose f goes from x to y is a function and that a is an element of a is a subset of x. We'll use the notation f of a to denote the image of a under f, namely the set elements in y, the set of elements in y that are image of elements from a. That is f of a is equal to f of a, which is element of y, and then a is element of set a. We can do this in the other direction as well. We might ask which elements of the domain get mapped to a particular set in the codomain. And then we would write f negative 1b for the inverse image of b under f, namely the set of elements in x whose image are elements in b. In other words, yes. Or wouldn't this work only if it's injective? Often we are interested in the elements whose image is a particular element y of in the codomain. The notation above works. F of negative 1 set y is a set of all elements in the domain that f sends to y. Makes sense to think of this as a set. There might not be anything sent to y, in which case we have this empty set. Or f might send multiple elements to y if f is not injective. As a notational convention, we usually drop the set of braces around y and we write inverse of fy instead for this set. So the is not an inverse function. Inverse functions only exist for bijections. But f minus 1 is defined for any function f. The point f minus 1 is a set, not an element of the codomain. This is just a sloppy notation for f negative 1 set of y. To help make this distinction, we would call f negative 1 y complete inverse image of y under f. It is not the image of y under f of negative 1, since the function f of negative 1 might not exist. Oh, this answers the question. But people usually represent this to be the inverse, right? If the bijection exists. Consider this function 1, 2, 3, 4, 5, 6. F of 1, 2, 3. Set 1, 2, 3 gives the output AB. From negative 1, AB is the entire set. And then D is an empty set. Set AB 1, 2, 3, 4, 5, and then empty set. Here is a summary of all the main concepts or definitions we use when working with functions. Functions are a rule that assigns each element of a set, called the domain, to exactly one element of a second set, called the codomain. Notation is f of x to y is our way of saying that the function is called f. To specify the rule for a function with small domain, use two-line notation. Then we have injective. Every element of the codomain is the image of at most one element from the domain. A function is surjective if every element of the codomain is the element of at least one element from the codomain. If every element of the codomain is the image of at least one element from the domain. Okay. We have this introduction to number theory in generating functions. How long is generating functions? Introduction to number theory. I'll definitely do that in the next stream. It will be the last stream considering this book. Okay, it's a small section. This is an extremely powerful tool in discrete mathematics used to manipulate sequences called generating functions. The idea is this: instead of an infinite sequence, 2, 3, 5, 8, 12, we look at a single function which encodes the sequence, but not a function that gives the nth term as output. Set a function whose power series displays the terms of the sequence. So for example, we will look at the power series 2, 3x, 5x squared, 8x cubed, 12x 4, which displays the sequence 2, 3, 5, 8, 12 as coefficients. An infinite power series is simply an infinite sum of terms of the form Cn x to the power of n, where Cn is some constant. I think they have a typo here. So we might write a power series like this. Ck is x to the power of k. So C0 plus C1x plus C2x squared plus C3x cubed. When we're in the context of generating functions, we call such a power series a generating series. The generating series generates the sequence C0, C1, C2, and so on, but only when x is 1, right? In other words, the sequence generated by a generating series is simply the sequence of coefficient of the infinite polynomial. What sequence is represented by the generating series? We just read of the coefficient of each x to the power of n term. A0 is 3. A1 is not 8. 8 is a coefficient of x square. So 8 is a term A2. So A1 is 0, right? A1 is 0. Okay, okay. Now you might very naturally ask why we would do such a thing. One reason is that encoding a sequence with a power series helps us track of which term is which in the sequence. For example, if we write the sequence 1, 3, 4, 6, 9, 24, 41, it's then possible to determine which term 24 is. If we agreed that the first term was supposed to be A0. However, if we wrote the generating series instead, we would have 1, 3 plus 3x plus 4x square plus 6x cube. Now it is clear that the 24 is the 17th term of the sequence. Of course, to get this benefit, we could have displayed our sequence in any number of ways, perhaps that did platforms, but we do not do this. The reason is that the generating series looks like an ordinary power series. So we can do things with it that we ordinarily do with power series, such as write down what it converges to. For example, from calculus, we know that the power series 1 plus x squared over 2 converges to the function e to the power of x. So we can use e to the power of x as a way of talking about the sequence of coefficient of the power series for x. When we write down a nice compact function which has an infinite series that we view as a generating series, then we call that function a generating function. In this example, we would say 1 half 1 over 6, 1 over 24. A generating function e to the power of x. I still don't get the use of the generating functions. The e to the power of x example is very specific. We have a rather odd sequence, and the only reason we know it's generating function is because we happen to know the Taylor series for e to the power of x. Our goal now is to gather some tools to build the generating function of a particular given sequence. Let's see what the generating functions are for some very simple sequences. The simplest of all 1, 1, 1, 1, 1. What does the generating sequence look like? It's simply 1 plus x squared. Now, can we find a closed formula for this power series? Yes. This particular series is really just a geometric series. Therefore, we see that this is equal to 1 over 1 minus x. Hold on a minute. Multiply, shift, subtract. This only works if x is below 1, right? If x is 1 or no, wait. This doesn't make sense. If x is a positive number, so 1 plus 2 plus 4 plus 8 is what? Minus 1? It would make sense if x is less than 1 because it converges, but this sequence diverges, right? So it doesn't make sense. You might remember from calculus that this is only true on the interval of convergence for the power series. In this case, when the modulus of x is less than 1. That is true for us, but we don't care. You're never going to plug anything in for x as long as there is some value of x for which generating function and generating series agree. We are happy. Let's use this basic generating function to find generating functions for more sequences. What if we replace x by minus x? We get this, which generates 1 minus 1, 1 minus 1. But we get 2, right? So if we do x is equal to 1, then it flips between 1, -1, 1, -1, 1, -1. But this answer will give half. We replace x by 3x, we get, okay, by replacing x in 1 over 1 minus x, we can get generating functions for a variety of sequences, but not all. For example, you cannot plug in anything for x to get the generating function 2, 2, 2, 2, 2. However, we are not lost yet. Anything that each term of 2, 2, 2, 2, 2 is the result of multiplying the terms of 1, 1, 1, 1 by the constant 2. So multiplying the generating function 2 as well, we get this, it generates 2, 2, 2, 2, 2. Similarly, to find the generating function for the sequence 3, 9, 27, 81, we know that this sequence is a result of multiplying each term 1, 3, 9, 27 by 3. What about the sequence 2, 4, 10, 28, 82? Here, the terms are always 1 more than powers of 3. That is, we have added the sequences 1, 1, 1, 1, 1 and 1, 3, 9, 27 term by term. Therefore, we can get a generating function by adding the respective generating functions. Just this. Why are we doing this though? The fun does not stop there. If we replace x in our original generating function by x squared, we get this, which generates 1, 0, 1, 0, 1, 0. How could we get 0, 1, 0, 1, 0, 1? Start with the previous sequence and shift it over by 1. But how could you do this? To see how shifting works, let's first try to get the generating function for the sequence 0, 1, 3, 9, 27. We know that 1 over 1 minus 3x is 1, 3x, 9x squared, 27x cubed. To get the 0 out front, we need the generating series to look like x plus x, 3x squared plus 9x cubed. So there is no constant term. Multiplying by x has this effect. So the generating function for 0, 1, 3, 9, 27 is x over 1 minus 3x. This will also work to get the generating function for 0, 1, 0, 1, 0, 1. Here's a sneaky one. What happens if you take the derivative of 1 over 1 over x? 1 over 1 minus x. We get 1 over 1 minus x square. On the other hand, if we differentiate term by term in the power series, we get 1 plus x square plus x cube differentiated, which is equal to 1 plus 2x plus 3x plus 4x cube, which is the generating series for 1, 2, 3, 4. This says 1, 2, 3, 4, 5 is 1 over 1x square. So if x is 1, then we get 1 over 1 minus 1, which gives an error. Take the second derivative, 2 over 1 minus 1 minus x cube. This is the generating function for the triangle numbers. We have seen how to find generating functions from 1 over 1 minus x using multiplication, substitution, addition, and differentiation. To use each of these, you must notice a way to transform the sequence 1, 1, 1, 1, 1 into your desired sequence. This is not always easy. It is also not really the way we have analyzed sequences. One thing we have considered often is the sequence of differences between the terms. This will turn out to be helpful in finding generating functions as well. The sequence of differences is often simpler than the original sequence. So if we know a generating function for the differences, we would like to use this to find a generating function for the original sequence. For example, consider sequence 2, 4, 10, 28, 82. How could we move to the sequence of first differences 2, 6, 18, 54? We want to subtract 2 from 4, 4 from 10, 10 from 28, and so on. So if we subtract term by term the sequence 0, 2, 4, 10, 28 from 2, 4, 10, 28, we will be set. We can get the generating function for 0, 2, 4, 10, 28 from the generating function for 2, 4, 10, 28 by multiplying by x. Use a to represent the generating function for 2, 4, 10, 28, 82. We have this, a minus xa, then we get this. But we don't exactly get the sequence of differences, we do get something close. This particular case, we already know the generating function a, but most of the time we will use the difference technique to find a. If we have the generating function for the sequence of differences, we can then solve for a. In each of the example above, we found the difference between consecutive term which gave us a sequence of differences for which we knew a generating function. We can generalize this to more complicated relationships between the terms of sequences. For example, if we know that the sequence satisfies the recurrence relation an3, an minus 1, minus 2, an minus 2, in other words, we take a term of the sequence and subtract 3 from the previous term and then add 2 times the term before that, we get 0. That will hold for all but the first 2 terms of the sequence. So after the first 2 terms, the sequence of results of these calculations would be a sequence of zeros for which we definitely know a generating function. What happens to the sequences when you multiply 2 generating functions? Let's see a is equal to a0 plus a1x plus a2x squared. To multiply a and b, we need to do a lot of distributing. But keep in mind, we will group like terms and only need to write down the first few terms to see the pattern. Constant term is a naught b naught. Coefficient of x is a naught b1 plus a1 b0, so on. We get ab is equal to a0 b0, a0 b1, and plus a1 b0. So multiply with the sequence by the sequence this. Multiply 1 with all of them, 2 with all of them, 3 with all of them. Wait. 0 b0, a0 b1, a1 b0. So 1 times 1 and then 1 times 2 plus 2 times 1 and then 3 times 1 plus 2 times 2 plus 1 times 4 and then 4 times 1 plus 3 times 4. So 4, 1, 3, 2, 2, 4, 1, 8. The front from here is going from the back of from here. One times 2 plus 2 times 1. 1 times 4 plus 2 times 2 plus 3 times 1. Okay. So if it's like 4, then the fourth term here multiplies with the first term here. Third term here multiplies with the second term here. Second multiplies with the third, and the first multiplies with the fourth. So we are going in reverse orders. I'm rushing through this because I don't really understand the use of generating functions. I think maybe if I go more in depth later on. We conclude with an example of one of the many reasons studying generating functions is helpful. We can use generating functions to solve recurrence relations. Solve the recurrence relation an 3, an minus 1, minus 2, an minus 2. With initial condition a0 is 1 and a1 is 3. You saw in the example above that this recurrence relation gives the sequence 1, 3, 7, 15, 31, 64. Okay, we can just plug in the numbers which has a generating function 1 over 1 minus 3x plus 2x square. Wait, did we calculate this? They talk about it here. The sequence 1, 3, 7, 15, 31, 63 satisfies the recurrence relation. This, find the generating function. So a is 1, 3x, 7 square x. Minus 3x gives us this. Plus 2x square gives us this. So 1 minus 3x plus 2x square, a is equal to 1. So this is the generating function. We did this by calling the generating function a and then computing a minus 3xa plus 2x squared a, which is just 1, since every other term cancels out. But how does knowing the generating function help us? First, break up the generating function into two simpler ones. For this, we can use partial fraction decomposition. Start by factoring the denominator. Partial fraction decomposition tells us that we can write this fraction as a sum of two fractions. This plus this for some constants a and b. To find a and b, we add two decomposed fractions using a common denominator. Okay, they found a, b, then what? This completes the partial fraction decomposition. Notice that these two fractions are generating functions we know. In fact, we should be able to expand each of them. So this generates to minus 1, minus 1, minus 1, and then this generates to 2, 4, 6, 8, 16, 32. So we have 1, 3, 7. We can give a closed formula for the nth term of each of these sequences. This is just an is equal to minus 1. The second is an is equal to 2 to the power of n plus 1. The sequence we are interested in is just the sum of these. So the solution to the recurrence relation is an is equal to 2 to the power of n plus 1 minus 1. Okay, I can see the helpfulness at the end, but I need more practice with this. I think next stream I will do a number theory. This should take around 1 hour, I guess. Yeah, I will end the stream here then. And yeah, see you guys next time. Bye.